Gonna switch things up on you here and speak from the left microphone. I like working from my presenter's notes and I just couldn't work it out here. So I apologize if this is distracting to be on this side. But as Sebastian has said, so my name is Kevin McGouldrick. I'm at Laboratory for Atmospheric and Space Physics. If I'm in presenter mode, I better be in presenter. And yeah, I want to speak about Venus atmosphere, microphysics, and clouds. But first, I want to just call attention to the background. Advance both slides. It's a background image that I like to use. And admittedly, this is getting to be a bit out of date. But the 4 quadrants here display data from 4 different wavelengths and 4 different missions. So Magellan in the upper left, Pioneer Venus in the lower left, Messenger from a flyby on the way to Mercury in the upper right, and Galileo in a flyby on the way to Jupiter on the lower right. And although my focus today is on the atmosphere, it's important to remember that there's still a great deal to be learned about the surface and interior of both past and present Venus from the exploration of its solid body. So recently selected missions such as Veritas, Da Vinci, and Envision will be investigating the surface and interior of Venus. Veritas and Envision through synthetic aperture radar, coupled with passive measurement of 1 micron emission. Da Vinci through detailed chemical analysis of the troposphere and surface composition during descent, troposphere and near surface composition during descent through the atmosphere. And while such investigations are absolutely vital to understanding Venus, as we were discussing yesterday, I would add that really it would be impossible to understand the nature of both current and past Venus without also understanding its atmosphere and clouds. And that kind of leads us to the microphysics. Venus looks very different at different wavelengths of light, as shown in this background slide. And these differences also play a significant role in the energy balance of Venus and our ability to measure both its surface and its atmospheric properties. These differences are strongly dependent upon the nature of the clouds, and that nature is in turn driven largely by microphysical processes. I've used the word already 3 times in this talk. But what is microphysics? So to borrow a line from many high school essay, and I apologize for this, it seems to mean many things to many different people. I'd argue though, my working definition is it's really the study of the governing physics that regulates phase transitions of atmospheric aerosols. And that's kind of a personal definition. There are many different ways to look at it. Speaking of definitions, an aerosol in the course of this talk, what I mean by that is a suspension of a solid or liquid in air. Larger aerosols become cloud droplets, can be termed cloud droplets or can be termed precipitation. But on Venus, where we have a cloud deck 50 kilometers above the surface, pardon the pun, these definitions get a little bit hazy. Microphysics depends on atmospheric structure, gaseous chemistry, aerosol composition, aerosol size, and aerosol phase. You see an example of Earth, just everything that's going on in the clouds. And many of these will require in situ sampling to really fully determine, but radiative transfer retrievals and microphysical modeling can provide some constraints. With apologies to the doctor, it is not a big ball of wibbly wobbly, timey-wimey stuff. It is a big ball of wibbly wobbly, timey-wimey integral differential equations. It's very difficult to incorporate all of this physics at once. This is why oftentimes, even though it's very vital to understanding atmospheric dynamics and radiative transfer, usually there are a lot of shortcuts taken with cloud microphysics, understandably. We wouldn't have any answers from the models if we put everything in there. But at the same time, we see all of the coupled processes here. We've got, I'm not gonna go through, but in this, we see some on the top line, transportation terms, both from sedimentation and winds and from diffusion, often called eddy diffusion profiles in the atmosphere, production and loss mechanisms in the next line. Here we're talking about things like droplet activation and nucleation, production of particles through photochemistry, for example. Phase change falls into this as well when it comes down to microphysical modeling. And then the last 2 lines look at coagulation growth and loss of particles. And then the last term on the bottom line looks at the actual condensational growth and evaporational negative growth of particles. But we can look at these, and each of these terms is going to depend differently on the physical characteristics of the particles in the atmosphere. And so by considering changes in these, we can then execute codes that explore this differential equation and try to understand a little bit more about the governing properties, both of the microphysics and of the aerosols. But first, I want to just give a quick overview of the Venusian cloud decks to give you a sense of these clouds. So the atmosphere contains significant sulfur dioxide and water vapor, which combined with sunlight. Obviously, the chemistry is a lot more complicated than this, but I only have limited space on the slide. It will condense into sulfuric acid droplets, which will condense at all altitudes in which it is capable of doing so. Deeper in the atmosphere, it is warmer, and so the sulfuric acid returns to vapor phase. Deeper still, it is warmer still, and these vapors can return to their constituent components, sulfur dioxide and water vapor. Some of these vapors can also be replenished through volcanism. And because of both the radiative heating near the surface and cooling from the cloud top, you can set up a convective cell with a convection within the clouds, which actually leads to a breaking of the cloud structure into two separate decks. Right. A little bit of stability indicated through the potential temperature profile here. And then also there are hazes both above and below. And I'm going to go through each of these individually. It's kind of interesting looking at this slide. You kind of add to your model. This is kind of an example. You add to your model as you build it through your career. I've also been adding to this slide as I build it through my career. You should see the equivalent version that was in my thesis. It was much less complicated. Even though we knew all this stuff, it was just a matter of actually getting it in there and discussing it. So what do we know about the clouds? I want to start with the middle and lower cloud decks, or the convective or condensational cloud deck. Because the majority of the cloud mass is found here, mostly from LCPS. We understand that it's mostly most of the information we have of this is from the Large Probe Cloud Particle Size Spectrometer on Pioneer Venus. Microphysics, the majority of the aerosol mass is found here, and the mass of the vapor is comparable to the mass of the cloud at these altitudes. Microphysics timescales at this altitude are often measured in hours to days, and so the mass of vapor is comparable to the mass of cloud, but even still, these are much less abundant than the equivalent vapors in the atmosphere of Earth. So for example, you have 4% water vapor near the surface of the Earth on average. Parts per million is the operative measurement for the clouds of Venus. There are three modes of particles. Modes 1 and 2 are very likely sulfuric acid, known largely from in situ measurements. Mode 1 is submicron. Mode 2 at these altitudes a little bit more than a micron radius. Mode 3 seems to be a little bit larger, but some of this is uncertain. So Vega suggests that both the CCN, that mode 1 is composed of both cloud condensation nuclei, so involatile particles, and droplets at these altitudes. Mode 3 is most of the cloud mass, according to Pioneer Venus LCPS, but it is not necessarily consistent with spherical particles of sulfuric acid. In fact, that is probably the one most definitive thing Nolenberg and Hutton said about mode 3 is it is not spherical particles of sulfuric acid, yet it is, because it is easy to simulate in both radiative transfer and in microphysics. That tends to be the operative assumption. They could be crystalline. It could also possibly just be an extension of mode 2. In terms of it could just be instrumental error. In the Vega descent probes, about 10 years after the Pioneer Venus descent probes, actually these larger particles weren't even seen. And so the question is, does that implicate an instrumental error? Does it possibly just say that looking at the background, we can see a lot of variation in the near infrared image here? Are we just seeing weather on Venus between the two of these? Or are we just seeing differences in cloud growth? Now, was there ambiguity in the size distributions? On the right on this panel, we look at how Nolenberg and Hutton worked out the mode 1 best estimate. Really, there were only 2 bins of information from the LCPS instrument, and that's not enough to define a size distribution. And so they applied some very reasonable microphysical arguments to say, well, coagulation is a thing. These particles are going to grow according to coagulation properties over time, and so if they are very numerous, we wouldn't be able to observe them in a stable manner. And so they kind of balanced the microphysics and the observations to come up with a best guess estimate for the cloud particles, for the mode 1 cloud particles. The Vega data came along later, suggested that there could actually be a larger number of these mode 1 particles, even by an order of magnitude or 2, suggesting that maybe we need to revisit exactly what the microphysical properties are of these things. It's important to note we have no idea what the CCN are in the clouds of Venus. We know that there's sulfuric acid there, but all the other particle compositions are really unknown. And on the left, we're showing just a mismatch between the mode 3 data and the mode 3 fit. There was never really a very good fit, and this is kind of one of the figures that led Toon et al. To suggest that maybe there's just an offset between the 2, and that mode 2 and mode 3 really are the same kind of beast. Moving higher into the atmosphere, let's look at the oh, sorry, I forgot. So actually coming up later today, we're going to have a talk by Spacek looking a little bit at astrobiological implications in the atmosphere. But here on this slide, we're looking a little at a figure from Siger et al., looking at the life cycle of putative spore-like life cycle in the clouds of Venus. And on the right is a figure from LeMay et al., looking at whether or not this could potentially similar microphysics and physics could be seen in the upper clouds in terms of the unknown absorber. But really, this kind of puts this takes microphysics to another level. You thought my initial differential integral equation was complicated. You add particles that take an active role in their existence, and you get a whole new ball game. But it's important to show that yes, the microphysics of particles plays an important role in the distribution of the clouds and our understanding of what it is we are seeing, and can actually change a number of chemical parameters that we can observe otherwise in the atmosphere. Right, so yeah, moving higher into the clouds. Next most massive is the upper clouds. Here, the mass of the cloud is much more massive than the vapor. Sulfuric acid vapor pressure is so low that at saturation and at ambient, your concentrations of sulfuric acid are getting down to parts per billion to parts per trillion by volume. We know we're pretty confident in the identity of mode 2 at these altitudes due to polarimetry. They're particles of about 1 micron. The refractive index is consistent with sulfuric acid, and this is confirmed by in situ analysis. Mode 1 particles are submicron and possibly very numerous. This is one place where the Vega probes suggested that possibly the numbers are even larger than what was seen previously. What is uncertain, again, is the size and number of those mode 1 particles. The unknown absorber is mostly at these altitudes, it seems. We don't know what it is, but it seems to be here. It could also be an aerosol itself. There's recent observations suggesting that phosphine was detected in this region, perhaps pointing to aqueous chemistry or biology going on at these altitudes. The physical phase of sulfuric acid is an unknown, which I'll get to later on. Freezing or glass-like transitions are possible, which could have implications for lightning. Moving higher, the upper haze is essentially, we think, just an extension of the photochemical upper cloud. It typically is bimodal. It was initially thought to uniformly diminish with altitude, but more recent evidence suggests that there are detached layers around 78 to 84 kilometers seen by SWAR on Venus Express. And it appears as though there's an actual transition of the cloud top the cloud top altitude as a function of time of night or time of day, depending on how you want to count, on Venus between dusk and dawn, where the dusk haze appears to be higher in altitude than the dawn haze. Is this dynamics? Is this microphysics? Is this chemistry? Is this something? Is this observational? Who knows? There's still a lot of unknowns here. Continuing on to the unknown, the composition really needs to be inferred here. We don't have a lot of in situ measurements of these particles at this altitudes. The influence of aeronomic processes and dynamics will become important up here. We had some talks earlier this morning and afternoon looking at nitric oxide and oxygen, air glows and night glow, indicating that there's interesting dynamics and chemistry going on in these altitudes. It would be naive of us to fail to consider the implications of this on the aerosols as well. For example, nucleation through ionization, nucleation of new particles through that process is something that hasn't really been considered in existing models. Potentially would be important looking at the aeronomy that we have in this region of the atmosphere. And going down to the lower haze, really there's only one mode at this altitude, it's submicron. We don't really know the precise risk because it is so small. We have no idea what the composition is. We know that it's not sulfuric acid because it's far too warm for sulfuric acid down at those altitudes. And then as mentioned before, it is possible that this is a reservoir for the aerobiosphere based on the discussions by Seeger and all and others who have been attempting to model this. Actually phosphine being observed in the upper clouds, phosphoric acid is potentially stable below 35 kilometers, and others have suggested that some of the measurements by the SEM probes at those altitudes could be an indication of the existence of phosphor-bearing mineral components at those altitudes. Just giving a sense of what it is we're looking at, those of you who have been to LASP in Colorado will recognize this scene. The clouds of Venus have an extinction coefficient of about 1 to 2, on average about 1 to 2 inverse kilometers. This is an extinction coefficient of about 1 to 2 inverse kilometers. There is a building circled right about there. That is an engineering building on main campus. That's about 2 kilometers, I think about 1.5 kilometers away from East Campus. And it is just barely poking out, visible against the background snow from that day. So just give you a sense of what it is you would actually be experiencing if you were in the clouds of Venus. But this is also an indication that I'm now transitioning to actual observations and models in of the clouds of Venus. And so, yikes. Okay. I've got 5 minutes to get through actual work. Okay, so some work that we've recently done. So you had seen the talk by Sato Sensei earlier about the giant dark cloud seen in the giant, or its continuity seen by Akatsuki in the IR2 data. Javier Peralta looked and I looked for evidence of this in Virtus observations, and we found something that looks like it, and we decided, well, we can apply the work by others, people like Joe Barstow and Colin Wilson and Robert Carlson have all looked at rate of transfer analysis that can extract microphysical parameters and chemical parameters from the atmosphere. So we decided to look at this phenomenon through that lens, and what we found was that it was actually possible to see sharp transitions in these various both chemical and microphysical parameters that were extracted from the observational data that can tell us something about changes in the microphysical properties and changes in the dynamics at these altitudes in the clouds in the response to dynamical phenomena such as this. And so the point of this slide is that such remote sensing really, this is all from basically the 1 and 2 micron near infrared spectral regime of the emission of Venus. This can still tell us a lot of information about cloud properties, microphysical properties, and constituent species in the atmosphere of Venus, and especially so if you're able to couple that with in situ ground truth. So kind of giving you an eye forward to future missions that could accomplish such tasks. Looking at modeling questions, I had mentioned before the possibility of frozen phase changes in the atmosphere of Venus. On the right is a phase diagram of sulfuric acid in the domain of Venus. Temperature and weight percent. On the dashed line is basically an atmospheric profile. The numbers are altitudes. As you can see, small numbers are at the top, big numbers at the bottom. So if we really want to understand this, we should probably flip this and match it up with the cloud we have on the left. And so what we see here is there's a transition from where we cross the solid liquid line of equilibrium sulfuric acid phase right at about the transition between the upper and the middle clouds. So one thing that I considered a few years ago was, well, what if, I mean, when particles freeze, maybe they have a hard time sticking together, especially if they're glass-like particles, as opposed to, you think about maple syrup on a cold day. It becomes more rock-like, then it becomes crystalline, and more rock-like than it is like than liquid. Perhaps these particles are going to have the droplets are going to have trouble sticking together when they collide. So let's run a simulation where we basically prevent droplet coagulation with itself. And we found that if we did that, we did identify some significant changes in the size distribution for a model that was quote unquote normal, where we allowed the droplets to grow by coagulation, and on the right, where we did not allow the droplets to grow by coagulation. It turns out most of the change that we saw here was actually the result of cloud condensation nuclei then reaching into the upper clouds, where they then encountered extremely supersaturated conditions. But at the same time, if we just compare like to like from the left to the right, we do see significant differences in the size distributions. So, for example, you can look at the particle, the one micron and several micron droplets. Here, there's a clear separation on the coag var column compared to the nominal column. So this is just indicating that changes in microphysics can result in significant changes in the particle size distributions, which could potentially be measurable as well. More recently, this is a paper, it says in review, but just as I was getting on the plane, I heard it was accepted. We finished with the revisions. I was looking at in the upper clouds, we produce sulfuric acid by photochemistry. There's probably also many other solid species that are formed by photochemistry that could serve as cloud condensation nuclei, whether they're S2, whether they're unknown other results of the products of the photochemistry, who knows? But we have no idea what they are, and we don't really have a good sense of what their microphysical properties are. So what if those particles were unable to grow? They're formed and they might be nanometer sized particles. What if they're unable to grow to large sizes by coagulation? This is going to change how easy it is for the droplets to condense upon them, which is going to drive all sorts of different changes in the basic microphysics of the clouds. So this is just a comparison of two simulations in which we allowed these photochemical CCN to grow by coagulation or not. And we see that what this triggers is a difference in the cloud droplets. Cloud droplets, we didn't change the microphysics of the cloud droplets at all in this model. The only thing we changed was the CCN. And we ended up with a cloud which actually reduces the total opacity on average. So we're down to about 30 typically, compared to about 40. And we also began to trigger some longer term oscillations in the clouds. These are measurable. And so these are things that we could potentially look for in the clouds of Venus. Oh, there's a chat. I am going to skip, because I'm running low on time, I'm going to skip this slide because this is basically pretty much just showing this is showing the size distribution that we looked at before for the glass-like sulfuric acid case, but this is now for the non-coagulating CCN case. If you want to talk about it afterwards, just want to highlight a couple of places where there are noticeable differences. Sometimes the colors don't show up very well on a talk, and so that's another reason I want to just move beyond this one to my last slide, I want to point out the lab, in the laboratory is another place where we can look for microphysical properties that can tell us more about the clouds of Venus. So recently there was in the Planetary Science Enabling Facilities Program, Mike Pauken led a team that was one of the recipients of awards there to build the Planetary Cloud Aerosol Research Facility. This is going to investigate the formation, lifetime, and optical properties of planetary clouds and aerosols. So not just Venus, but a lot of us on the team were Venusians, and so that's kind of close to our heart, and that's we're hoping to learn a lot about that. Joe Salazar will be presenting a talk later today about, not about this, but about a related investigation at JPL, which is taking advantage of some of the same brain trust. He'll be talking more about exploring the influence of sulfuric acid on instrumentation. So I'll just put up my my conclusions here. Clear this. Okay. The point is there still are many unknowns remain in regarding the clouds and regarding the microphysical parameters in the clouds of Venus, particle sizes, compositions, and permutations thereof, chemical precursors as well. The need for improved or even dedicated in situ measurements, i.e. future missions of the atmospheric chemistry and physics, is really needed. The best ground truth we have is now getting close to 50 and 40 years old. There are 3 descent probes, Pioneer Venus and 2 from Vega. And so really only a handful of minutes of measurement. Da Vinci will be passing through the atmosphere soon, but there is not a lot of instrumentation there. There's not going to be a lot of information that we learn about the clouds themselves from Da Vinci. Simultaneous measurement, both in situ and remote sensing, similar to terrestrial field campaigns to study clouds on Earth, would be groundbreaking. And then I'll just highlight the bold-faced items on the right rather than read the full bullets. And as remote sensing via polarimetry and the near-infrared windows will be, I think, revolutionary. I think that's something we really need to really understand the clouds and aerosols of Venus, especially the chemistry and microphysics. Microphysical models of the aerosol, there are a number of groups out there working on these, especially those that include chemistry and rate of transfer processes, will really enhance our understanding. And really understanding real aerosols in the lab will help to parameterize these properties. I guess I did end up reading the bullets anyway, sorry. So, all right, thank you.